Ladies and gentlemen, it's time for us to conclude our Chapter 18 discussion with some loose ends. So what's going on here? Give reagents for the following, and we're going to use these 4 carbons to make a molecule that's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And it's the only source of carbons. Ooh, that should be fun. Yeah. I'm going to give you a nice hint. Aren't those 2 identical groups on an alcohol? When you see that as a, I guess you could call it a target, right? Here's what you should think. Ester, okay. All right then. I don't know how that happened. Ester plus excess Grignard. Oh, that's it. That's disrespectful. It is a guy's name after all. Now, when I say Grignard, there's something else that would do it exactly the same, right? What's that one? Oh no, the G's are not alike. That's the hard part because they have the G. You want to put them together. The Gilman and Grignard do not behave very similarly at all. But the Grignard and the organolithium, they can be treated identically in this class, and you will never have trouble, ever. I'm just reminding you that was from test 1. It's relevant now. Again, it's always relevant. So I'm not even going to write Grignard or organolithium, but they are synonymous in this class. So I need to make an ester, and those are my only carbons I'm allowed. Well, half of making an ester is an alcohol. We got that. The other half is what? If you're talking about a traditional Fischer esterification, which some of us have a test on in the lab tomorrow. Whoa. Sorry to be reminding you. What's the other functional group that reacts with an alcohol in a condensation reaction to make an ester? So how do I make that into a carboxylic acid? That's your first step. Step 1. How do you make that into a carboxylic acid?
Chromic acid.
Yeah, chromic acid. I'll give you half credit. Oh, he's so mean. You can't buy chromic acid. You got to tell me one of the ways to make it.
CrO3 plus.
Yeah.
H2SO4.
Yes, perfect. She said CrO3 plus H2SO4 aqueous. She's got it all. Oh. Yes. I was thinking of the esterification later. Sorry. I was thinking water's my enemy. But no, to make chromic acid, you have to have water. She was 100% correct. And now you got an acid. And don't forget, you still have the alcohol you started with. You didn't have to react your whole bottle, and you didn't. So here you got your butanol and say H2SO4. Now, this is where I was saying the water was not sitting well with me. You want the opposite of water here. What's the opposite of water? 3 initials, yes, DST. The opposite of water means, yes, water's being produced and I got to get rid of it. Yeah. Once again, DST is optional on your end. You don't ever have to show it to me. And now you got your ester. So now you've got the ester. Oh, that's bad choice. Let's go for a different color. We got the ester right here, blue on blue. Ester plus excess Grignard. Well, you're also going to have to make a Grignard from the same alcohol. Don't pretend to be the only person that knows how to make an alcohol into a Grignard. There's no person that knows how to do that. The only way you know how to make grignards is from organohalide. Step 1, make organohalide. You guys love PBr3, I know you do. Triple peanut butter. Now, how do you make that into a grignard? Here's your grignard. It's going to be BR on the end here. There's an MG in the middle. No, I need a chemical. MG and diethyl ether. There we go. So we got a grignard. And the reaction that's new is right now. Step 1, you mix these two things together. One, mix. I'll just give you a hint at the mechanism. Isn't this grignard the equivalent of a C-? And the arrows say step 1. You're not asked for a mechanism, so I'm not going to say red, blue, red, green. It's going to do it. That goes to a ketone, right? Grignard number 2 plus HCl. This is the grignard number 1 here. Looks like a 6. No, it looks like a G6. Don't make that anymore. Okay. Yeah. So you're going to get, when you see 2 identical R groups on an alcohol, easiest way was from ester and grignard. And step 2 is you got to get an H on your O-, because you're going to get an O- after the second grignard. HCl. That is consistent all semester, isn't it? If you use a grignard, what's your second step every time? HCl, protonation. Yes. That doesn't change all semester. Okay. Nice. Now, when you see a ketone, you can make that using a coupling reaction. Coupling. Now, one of those G words was used for coupling, right? The Gilman plus acid halide will undergo coupling to give a ketone. When you see Gilman's, coupling should be the first thing on your mind. So I don't have a Gilman yet, but you know, I can do what I did upstairs. 1, PBr3, 2, Mg@2O, 3, CUI. Nice job. She remembered. So that's going to give us this. That's supposed to be an arrow. To give 2, 3, 1, 2, 3, 4 with a CULI, and there's 2 of these groups. And that's a Gilman, right? We'll highlight it. We'll try. Good old yellow.
Number 2 should be Li with hexane
It could be.
or Mg.
It could be. She asked a very good question. She said, shouldn't step 2 be lithium with hexane? Yes, that would give the traditional Gilman with a lithium there that I actually put by mistake as habits, you know. But here the cation is just MgBr, and it's still called a Gilman. And so we have a different cation, MgBr cation. And now we better definitely highlight our Gilman. The Gilman is everything here. Yeah, you got 2 butyl groups on a copper, and that gives an anion, and MgBr is a cation with a +1. And to couple that, you need a Gilman, which we've got. But we don't have an acid halide, do we? How do you make an acid halide? Well, we know how to make the acid because we did that earlier. Let's just use that over again. We'll go in purple. Let's just do both steps. Acid halide is going to look like this. The only acid halide you know how to make is the chloride, okay? And one was the exact same thing we did earlier. 1 CrO3, H2SO4AQ. And how do you get that chloro on there? Cl. Well, it's got an OH on there after step 1. How do you convert OHs to Cls? It's the same in chapter 10. Nice. And chapter 16, that was 17, the end of 17. SOCl2. SOCl2, comma, PYR. What's PYR? Pyridine. And that's going to give us our acid halide. Let's go with a different highlighter. Light green, acid halide. Mission accomplished. And those highlighted things you can just mix. I don't even know how to say that. To say mix acid halide plus Gilman. How's that? Mix acid halide plus Gilman. And you got ketone. The Gilman carbons ended up with a halogen one. That's coupling from test 1, isn't it? They did. So finally finish the chapter here from 18.4b and 18.4c. I got a statement down there. Recall, chapter 9. Cyanide is a... Yes? Yes. Thank you. Who was that? Nice job. Strong nucleophile. So if I had a carbon with a leaving group on it, I would just mix those two together. Right now, I don't have a carbon with a leaving group on it, but on this page already 2 times I've converted it to a carbon with a good leaving group. Can we do it one more time? PBr3. You're almost done. That's going to be a BR there. And then how about KCN DMSO? What good is DMSO? It's just a good solvent for SN2. I want an SN2 reaction. Got a primary carbon with a leaving group. Take that review to the max. Primary RX, strong new polar aprotic solvent. SN2 all the way. Every piece said SN2. It's just a really nice way to make a nitrile. Yeah. Another way to make a nitrile is from, hey, we've seen this already. What do we got over here? Primary amide. Can you tell me how the formula changes? Because that's a big hint at what needs to happen. What changes in the formula? I want the elements put together in their most common form. H2O, water. I like all your answers. Yeah, we're making this thing lose water. What's that called? Yeah, say the D word. Yeah, dehydration. So you think you might have what, sulfuric acid and heat? You get some of the product. You would. Sulfuric acid is not that great a desiccant. There's a much more powerful one. You got to learn it. It's the only time you're going to see it. It's right here. These two chemicals, P2O5 or the dimer, P4O10. Powerful dehydrating agents. They just strip water off stuff, and the mechanism it's beyond what we are going to do. So all P2O5 is good for is to take a primary amide, remove water from it, and make it into a nitrile, right? So one way to make nitriles is to dehydrate a primary amide. That's the one on the right. And another way to make a nitrile is to do an SN2 reaction on a carbon with a leaving group. And that'll make one with one more carbon, right? Oh, it's all good. This is all good. So amide with the same number of carbons, becoming a nitrile with the same number of carbons is what I should have said. You go that way. One less carbon, you needed to make it into a nitrile. Make this into a primary carbon with a leaving group. Then SN2, there's your extra carbon. And there you go. Okay. I think we're going to do another loose end video right after this because I just had an idea.